Okay, for completeness, we'll bring it back from the start.
Sure.
Basically, what we start with is a point, basically a sketch body of the suspension. So we have our shocks and everything. We have our contact points. We have our wheel centers. And we have basically all the information we need from the geometry of the car. And then with that in our testing, we were able to get some good data that calculates load transfer. So this basically takes overall vehicle accelerations and turns that into contact patch loads. So basically the forces acting on the car at the ground. Here. Basically, we did these tests and recorded vehicle acceleration and filtered out that data.
Also, one more thing. Can you describe which like test did what? Like, what is a skid pad test?
Skid pad is you drive in a circle. You just drive in a really big circle, so you're constantly have a lot of like lateral load, trying to see how fast you can drive in a circle without slipping. So if you look at that data, skid pad, yeah, it's purely lateral loads.
And then what's slalom?
Slalom is you have cones set up like I did like 2 parking spaces apart, and you basically zigzag between them.
Okay, got it.
Acceleration braking is simple. Curb strike is basically driving into curbs, so you get really funky loading. So we have lateral and vertical, or longitudinal and vertical acceleration. Crooked jump, self-explanatory. Abuse jump, self-explanatory. Abuse cornering. I don't really know how we got abuse cornering. I think it was just trying to see how hard you can turn without flipping the car. So basically, the process of the design is taking those loads, the test data from the car, and filtering it and figuring out how to design your parts accordingly. So we started with vehicle acceleration, and then you can use load transfer mechanics to figure out your contact patch loads. And then you can do some statics to figure out if you translate those forces to the wheel center, what would they be? So you take your 3 forces and then you translate them up to the wheel center. So you add a few moments in there to account for the displacement. Then with that, you can do some funky matrix calculations to figure out loads going through all your links. Do we want to run through this? This is kind of getting ahead of ourselves.
Yeah, that's okay.
So once we get this table here, which is stuff we calculate and we filter out. There's like Julie had made a MATLAB script to plot these and filter out like the low frequency stuff. And then basically these blue parameters you can change. This is what you would put in from what we gained before, and then this stuff you'd measure from the car. Same with this. Like I said earlier, arrow parameters we're just gonna neglect. And then springs, that's something we should validate in the future. Then once you get that, you spit it in, and it'll spit out 3 forces, and then the difference, because you have like your static load from the vehicle just sitting there, and then you have the extra load from bump, right? So now we're going into matrix stuff. Basically, this sheet takes all of the hard points that we got from the SolidWorks model, and you do some matrix math. And what you do is you take your tire forces that we got from this with our load case, like the acceleration, you take that, you plug it into here, and then holy fuck, I keep getting SolidWorks notifications. Stop it. Okay. Then this will spit out your link loads. So these are the forces acting at each of these points. So this would be going through the forelink, the aft link, upper, lower, and then your tie rod and your push rod and tie rod. Your push rod is your shock. I should change that too. And then once you get these, you would translate it and fill it into the row here. So if you look at this, this is for our abuse jump case, I'm pretty sure, for the front here. No, what is this? $11.75. So you have X inside.
It looks like curb strike or something.
This is braking.
Oh.
So X minus meaning towards the back of the car, and then also vertically pointing up.
Yeah.
So if we put those in, you leave this as 0 because you don't have data for this. This is the something to do with your tires, and we don't have the data for the tires. Basically ignore it. It's more important in road cars.
How would you get that data?
Well, we leave it at 0 because we don't have the data.
It would be like using a wheel force transducer to get the tire data.
Yeah, it's basically like how the tire like folds over and deforms as you're cornering.
Okay.
Like for the Formula car, they get their tires directly from the manufacturer, which provides that data. I don't know. Yeah. Not as important for off-road because of the low grip environment. Anyways, for each load case, you would then punch in from your load transfer calculator. You take your accelerations, put those in here, and they would spit them out down here. And then you'd take these and you'd plug them into this table, these two tables here. Basically, it's the same table over and over again. It's just this is the rear and this is the front.
Yeah.
So like everything below this separates front and rear. You take this and then you put it into here. So these, see how these match this?
Yeah.
So you do that for all your load cases. And then we can figure out like min, max, like which ones are going to be the worst. These two columns here are grayed out because they're the upper control arms, which have the shock mounted to them.
Okay.
So this is treating each of these links as a 2-force member. Basically only like tension compression going through these links. So like you'd have an axial force pointing in the direction of the sketch here, right?
Into the sketch?
Well,
is it into the sketch? Or into the laptop? Or
it depends what you're looking at. But for example, this link here, you'd have forces acting along that link. That's it.
Okay, so like negative y.
Or
would it be like perpendicular to kingpin?
They're 3-dimensional.
Okay.
Yeah, so here's a good example. So they treat it as a 2-force member. So we have our 4-link, which is an axial force going through this link here, and then we have the aft force going through this link here. But this calculation assumes everything is a 2-force member, but for the upper control arms that bear the shock, it's not a 2-force member. It's combined loading, right? Because you have like tension compression, and then you have your shock load as well.
Right. Yeah.
So these are grayed out because you shouldn't directly use these. You have to do some extra math. Our assumption of treating these as like 2-force members is, I wouldn't say 100% correct, but it's good enough.
And so the only difference right now is that you didn't include the shock force?
As of right now, yeah.
Okay.
As of how I'm explaining it?
Right, yeah.
So basically, once you plug in all of your accelerations for all of these load cases and fill in this table here, or no, this should kind of go here. So once you have your hard points and you have this data and you put in your accelerations, you can get your contact patch loads, which we then populate into this table here. So the color scale shows you basically it's 3-way, so it goes from green as positive to red as negative. So dark values are high forces. So if we look at our abuse jump, which is a 6G load landing, like 5 kilonewtons, 5.5 kilonewtons in each, which is a lot.
Yeah, that's very high. And that's just on the lower control arms too, right?
So this is just front and rear. So this is forces acting here on this trapezoid, the contact patch.
Okay, got it.
So the math we're doing is basically taking this contact patch force, translating it up to the wheel center here. And then with that, you can do your matrix calculation to figure out the reaction forces through all of your links.
Yeah. Okay. Yeah.
So then for links that we calculate as two force members, we can then go into, so big warning label up here.
Yeah.
Do I need to zoom in here?
I can see. But this is much better.
Okay, so this is just a copy of the last table from the previous sheet.
Mhm.
And then, so this is basically, we're doing a rough sizing for our tubes. So these are menus. You can pick different tube sizes that we carry.
Yeah.
You can see there's like 1/2 inch and 5/8 and 3/4. Those are,
Yeah, that'd be crazy.
yeah, like these are formula spec. You can see here shock is nothing because we're not sizing that. You can use these rough values for sizing the tubes initially for everything that's a 2-force member. It's a decent baseline for the upper control arms anyways, because you need them to survive that axial loading. Basically, this just calculates your factors of safety for everything. So if we look at this is taking the worst loads for each link. And then it's calculating your factors of safety for tension, compression, buckling, and then eccentric buckling.
Wait, so your factor is like 170?
Where?
Like where it says tensile FOS?
Yeah, because steel is good in tension.
I see. But like you don't have like factor of safeties of like 3. It's like like 6 to 9 to 11.
But then if you look down here, because these aren't like the governing load cases for these members, it would be buckling and then eccentric buckling. These are crazy. But once again, these are like, we shouldn't really be using any values from this column here. It's these that are more important.
Right. Okay.
Because these two are the
The
upper control arm.
Upper control arms. Yeah.
So we
still like 5 is high.
This is just to make sure like that we don't do all the work of designing a control arm and then putting it in ANSYS with something that's like going to break immediately.
Okay. Yeah.
So like these are already super thin tubes. Like these are 35 thou.
Right.
And this is just the same thing for the rear. Basically, play around with these numbers until you see something that's all right. Then this is basically figuring out these 4 sheets here are for your upper control arms to include bending.
Okay.
So you can see this has a much lower factor of safety against bending. And for the reaction forces, we assumed it was like a 50-50 split for the front because the shock is more or less acting the shock is more or less centered between the 2 hard points. in the front.
Yeah.
But for the rear, the shock is like disproportionately, like it's not centered at all, right?
Yeah.
So for the rears, what do we do here? Basically 1/4 is like the moment ratio lever arm is 3-to-1. So from here, from the shock to the fore link is 3 times longer than the aft hard point.
Yeah.
So you'll get 3 times the forces on the one side.
From which side, the fore or the aft?
The aft one will take more force because it's closer.
Okay. Yeah.
Is that true? 517. Yeah. Like the fore link on the rear, minimum factor of safety of 5, and the aft link like 1.8. There's some kind of sus stuff going on here, some assumptions, like the angle between the shock and the control arm. Like in the rear, that's a pretty like sharp
Doesn't
angle.
the angle,
the angle matters a lot.
like this is at ride height, right?
No, this is at full bump.
Okay. Why is it at full bump? Or like, yeah,
assuming,
why are we measuring it?
Because during a 6G landing, we're assuming that our shocks are basically going to max out.
Yeah, got it.
More or less. Like we're going to use the full displacement of our shocks. We can come back to this afterwards.
Okay.
And then it was nice to have all of those loads like those axial loads, but to know the like vector of those loads and putting them into ANSYS is kind of like long. The easiest way to do it is to break down that vector into like components like X, Y, Z.
Right.
So that's what these 4 sheets do.
Oh, I see. Okay.
So basically, this is a recap of the like magnitudes.
Mm-hmm.
And then we get our unit vectors for each of these. And with that, we can calculate the component loads. So we look here. Yeah. Anyways. So you have to do this for all 4 control arms.
Okay.
You can take
Got it.
You can take this and go into ANSYS and run it.
So I'm a little confused. Why can't you just use the vectors that you found on your Excel directly into ANSYS? Because they have like 2-dimensional vectors. Is it like a different coordinate system or a different, a different axes?
I don't know. Julian made the sum. But
okay.
It's important to maintain like the SAE coordinates in ANSYS. So basically to do that, you need to basically make your part. So we're looking at the rear upper. You take this, and you take your hardpoint file. You make a new assembly with your hardpoint file, fix that into place, and put your control arm, like mate it to the hardpoints, and then export that as a step file.
Okay.
So that it maintains the axis system of the like SE coordinates where we did all our calculations.
Okay.
So if you look at the rear upper, the origin of the rear upper is the origin of the assembly. You follow me here?
Yeah.
So see how the origin is way over here?
Yeah. So like you can export this as a step file. It'll still have the same origin, so that when you apply the loads, and you keep the same axes, like it will be in roughly the same position.
Correct.
Is that okay? Yeah.
So basically, you take that hardpoint file and you drop it in to the part file for your control arm. So it'll import in all these sketches.
Yeah.
And then you need to make some new local coordinate system to then do all your sketches off of.
Okay. Why do we need the local coordinate system?
Like you can do it so that your origin of your control arm is like whatever. It could be like one of these hard points.
Okay.
But then when you go and you drop it into your assembly, you go, okay, now where do I mate it to? Right? Because you could pick your origin to be like the center of the space here, or you could pick it to be the center line, like the halfway point of this tube.
Right.
You know, like there's some discrepancies, but if your origin is the origin of the assembly of the full vehicle, then there's only one position for this control arm to go in.
Okay. Yeah. Got it.
And
so the local origin that you added is just so that it's easier to make the part itself?
Correct, yeah. So if you look at mates in here, the first one is mating the origin together.
Yeah.
And that fixes everything in place. The rest of these are just for external parts, like the ball joints and shit.
Yeah.
The fronts, I think, are super scuffed still, because whoever did the CAD on these did it in a really like stupid. Sorry, I shouldn't say that. The person who made the CAD.
Oh my god.
Did not do a very nice job, and I didn't want to fix it.
Okay.
If you look at this, the front upper left is just a mirror of the front upper right.
Yeah, I see that in the features.
But then if you look at the front upper right, it's a mirror of the front upper left.
What the hell?
So there's just some like circular geometry or circular reference. I don't know. It's a little broken.
That's crazy. Okay, got it. In SolidWorks, God we trust.
Yeah. Anyways, so basically all the heavy lifting gets done here at this stage.
Yeah.
And hopefully this will help speed everything up substantially in the future.
Yeah. I guess in future situations, right? We have we have positions for the control arms based off of like whatever optimized position there is. But we just still have design. How would this capstone be of use in that situation? Or would this be more of like you get last year's control arms, you get the data from there. And then in future control arms, we use that data to basically make them more reliable.
I think the latter option is probably the way to go for now, until we have the ability to do like a full like multi-body dynamics and understand suspension kinematics properly.
Yeah.
Other than just like looking up what appropriate values are for certain parameters and using them.
Yeah. And then also, like this calculator is really useful and really helpful. But then how did you use these values to like get like what is our like ideal scrub radius, or what is like the best optimized part for like an upright or a wheel hub?
So this calculator is only doing control arm design.
Okay, got it. Yeah.
I think the best way to understand hub and upright design would be to do one of these calls with Julian and have him record it as well.
Okay.
Since he's the one who actually designed it all. Like designed the hubs and uprights.
Yeah.
Basically all of this work is assuming the kinematics are good.
So I guess with your control arms that you guys made, we should do the same thing that you guys did with the previous control arms. Put it in the calculator and then like see what values kind of pop out and adjust future control arms based off of those. And obviously with the like new shocks.
Yeah. So like what would be a good thing to do is rerun the vehicle test.
Yeah.
And get new like max accelerations, because odds are those values will be different now.
And then one other thing I'm a little confused on is how did you get the IMU data, the accelerations, into the forces, the contact patch force? Can you just repeat it one more time?
It's just a load transfer calculator that uses like weight distributions and like vehicle geometry.
Okay, got it. And then you assumed that the weight distribution between the front and the rear was 50-50?
What does it say here? Yeah, pretty much. Here's like 51-49.
Okay, yeah.
And then with like the vehicle parameters and your accelerations that we measured with the IMU, then it can figure out the forces acting on the car, the contact patch.
Okay. And so just to go into more of like the specifics of the math, is this also like a giant matrix? Or is this like some sort of differential equation?
I don't know. Julian did this.
Okay, got it.
I think it's just a few equations.
Okay. Yeah, sick.
The real heavy math happens in the like on this sheet here.
Yeah. That is one inverse matrix.
Yeah.
Ooh, tough stuff.
But it's built and it works.
Nice.
Yeah, so then basically we only did component level simulation. We didn't do assembly level simulation. because I couldn't get it to work with all of the like connections and contacts in ANSYS. Like I could get it to play nice a little bit, and then it would just say like crazy deflection detected or crazy displacement detected.
Okay,
like
got it.
So what we do is have cylindrical supports, and then we would prevent the control arm from just rotating about these cylindrical supports, and then apply our loads.
Yeah.
And basically, after running them for all of the control arms on all the load cases, this is a not empirical. I guess it's empirical, but it's just like a 1 to 10 value of how severe it is.
Okay, got it.
So basically, the load cases with reds are high severity. Basically, anything with a jump on the upper control arms that have the shock, like that's where we see the highest loads. This is a video. With this is a PDF, so it won't show up.
All right.
Basically, yield strength of 4130 is 435 MPAs.
Yeah.
Oh, and you can see here our max. Our max is really high, but it's like a singularity at the tips here. So we're looking at basically where is it actually bad, and it's bad right in the joint here. We're exceeding yield, and then if you account for the fact that there's going to be a big weld here, we will have like a weaker material in here because of the heat affected zone.
Yeah.
And so for the heat affected zone, we just assumed like a mild steel with a yield of, what is it, like 350?
Like, yeah. I'm gonna say, or
350.
Yeah.
These are all videos, which kind of sucks. I should have pulled it off. Anyways, to help prevent the super high stresses along all the welds, we put in this gusset. In reality, we didn't actually make this gusset. This purple one here.
Okay.
So hopefully it doesn't break. Anyways, made some changes. That gusset made it 26% better. This is factors of safety for each leg case. So we get like 16s on some of them, and then like your lowest is like 1 point something.
Right. Why do you think it is that our crooked jump actually got worse? Like slightly.
I have no clue.
Okay.
If you round it to one decimal point, it's the same.
It's the same. Fair enough.
That was assuming the whole thing is made out of like 4130. And for the heat affected zone, we just assumed all of these peak stresses or minimum factors of safety are in the heat affected zone anyways.
Yeah.
So these aren't necessarily all that representative. But these are because the heat affected zone makes it weaker.
Yeah.
And so we were advised by Professor Gooch to use basically just assume that it's mild steel because from what I understood, you can't get any weaker than this.
Oh, really? So if you weld with 1020 and then you have heat affected zones, the heat affected zones would also be like as fragile as 1020.
That's kind of what I think.
Okay.
So that's good. We are good against like static analysis. So the next thing that we looked at was fatigue.
Yeah.
So basically we watched a video of where is it? Basically went through this video and counted every time there was a certain obstacle. So like that'd be like a curb strike right here.
Yeah.
Basically count out how many times you'd see a certain obstacle in a lap of endurance.
Okay.
And CWRU finished first in this. So we took them to assume their pace. So based on one lap, based on how many laps they did, which they did 48. And we designed this to be able to withstand 2 seasons of driving. So this is how many of these events we'd see during endurance over 2 seasons, assuming we finish the race. So you can see we have like 11,000 curb strikes and only like 1,000 of each jump.
And so I see for 2 seasons, like it says 20 days, 4 hours, 80 hours of testing. Is that what 2 seasons of testing would be? 80 hours?
That's assuming we get 20 days of testing and we test for 4 hours each day throughout the season.
So it would be 160 hours total.
No, it'd be 80 hours.
80 hours. Okay.
80 hours, and then what is it? 4 hours. So I think we were doing like 100 hours. Is basically 2 seasons.
Yeah.
So then, based on how often we see those certain obstacles in endurance, we would allocate an equivalent percentage of testing time for those obstacles.
Yeah.
Like if we see 10,000 curb strikes, like rock gardens, logs, stuff like that during endurance, we better make damn sure that we are good at driving over those. So we allocate the most time for testing on those. And I made them nice numbers because 6.43 is not a nice number.
Yeah.
So assuming 10% of this 80 hours is spent testing abuse cornering, we have 8 hours of testing for that given event, given obstacle. What is this? This is the how many of these can you do in an hour?
Oh, okay. Got it. Yeah.
You can do at a pace of endurance. So at the pace that CWRU is driving, how many of these jumps can you do in an hour?
Yeah.
And then this is basically dividing everything by 2, assuming that like half of this time is spent not driving.
Mm-hmm.
So in an hour, we would realistically only do 66 abuse corner load cases instead of 132.
Right.
And then this just multiplies how many can we do in an hour times how many hours we're planning on testing, I think. Right? Yeah. And basically, we get this table of like which obstacles we see the most of, and how many of these events should the vehicle be able to withstand over 2 seasons. You following me?
Yeah. So
Um,
then we have the total cycle count for the 2 seasons, and then you're going to use that for the fatigue calculation, right?
correct.
Okay.
So then basically, from our peak stress from earlier, we can then look at SN graphs. Basically, go over until we get the line, and then go down and figure out how many cycles we can get. Do that for everything. A lot of it ends up being infinite life, which
Oh, really?
makes sense, right?
Yeah.
Because we design it to have like a factor of safety of like
Right,
2 on
like a
this.
bajillion. Yeah.
We'll end up with like a factor of safety of bajillion on that.
Yeah.
So what is this? This is 30,000.
And then that would be abuse jump. Okay, got it.
So this can withstand 30,000 abuse jumps in theory.
How did, like, if you go to the Excel spreadsheet, we had the curb strike jump jetting. Oh, okay. So if we did, like, if every single jump was an abuse jump when we were doing testing, what would that withstand? Is that correct? Is abuse jump like worst condition possible?
Abuse jump is a 6G landing. In testing that we did for this capstone, the max we would see is like 3.5.
Okay.
But that is also that was a baby jump into grass. Right? Like
Right. So did you guys ever test on concrete and see what the abuse jumps got to, or?
no.
Okay.
I think
Do you think 6G is like about an approximate of like what that would look like if it was just like a big ramp into concrete? Or is that still an underestimate?
I think it's probably an overly conservative estimation. Like I don't think we'll ever see 6Gs.
Okay.
Unless you're like sending it to a drop.
Yeah. So this is like if we were to do the worst case situation for 2 seasons of abuse jumps, what would our cycles be?
This is that.
Okay.
Okay, so yeah, I see what you mean. In 2 seasons for the abuse jump stress, or basically for the abuse jump, we can do up to 10,000 cycles.
Okay. Yeah.
For the rears.
And then
I think the fronts were better.
Okay.
Okay. Yeah.
Is this friend?
Basically, the fronts have infinite life for fatigue, so there's like still some optimization that can be done with that. Like we can bring that down.
Right.
Either make the tubes a little lighter. I don't know. But the goal isn't to like make the lightest thing possible. The goal is to finish endurance.
Yeah.
Basically, as long as this number is bigger than this number, we're good.
Okay.
If we expect to see more cycles than we can actually handle based on fatigue, then that would be bad.
Got it. Okay, got it. Yeah. So we're pretty much well above all of these right now.
Yeah, basically, if you could use those control arms for 6 years, 6 seasons.
Okay.
That's not important stuff. The one very big assumption that we made in terms of analysis was that every single one of the events we assumed to take place at ride height.
Like when you're on the ground? Like what do you mean?
Like, as in the car is just sitting on the ground statically.
I see.
Like we account for load transfer, but we don't account for the actual displacement of the control arms. You know what I mean?
Yeah.
So we assume, like, say we're taking a 6G jump, we're calculating the forces as if the car was just sitting on the ground.
Okay.
Which is inherently incorrect, right?
Right.
But it's a starting point. Like, there's room to make that better in the future. So for my the course for the student design teams, Genie 499, I chose to look at basically stuff on our capstone. So my whole investigation was basically, how important is it that we do our analysis at the specific positions of the control arms that they would see for an event? It's like, can we get away with assuming everything is at ride height for analysis? Or do we actually have to, like, consider the fact that the control arms will be pivoting and compressing the shock?
Right.
You following?
Yeah.
Okay, so I took 3 load cases that do different things. So I took abuse jump, and I took braking and acceleration.
Yep.
So this column here is the calculation of the forces. Yeah. Well, these 3 would be at full bump, and this one would be in rebound.
Okay.
So for acceleration, we're looking at the rear lower control arm, because that's the control arm that would withstand most of the torque caused from, like, pushing the tires against the ground.
Right.
You know what I mean?
And so you chose it to be like rebound because when you accelerate, like
we have a little bit of anti-squat, which would basically raise the rear end. I didn't calculate how much anti-squat, so I just assumed basically it lifts the rear of the car by 1 inch.
Okay, got it.
Whereas the rest of these max out the shocks, which for braking is probably not true, but for 6G landing, it's probably will be maxing them out. Yeah. So this was, let me see if I can find it here. Basically, this is another assembly I made. What? This is an assembly I made that has all of the sketch bodies that were like made from copies of the hardpoint file, but that are flexible.
Right.
You know, so that you can move it up and down. So then like I made 3 configurations. So we have rebound, full bump, and then 1-inch rebound. So this dot here is the contact patch, and this is the theoretical ground at ride height. So you can see
Sorry,
this.
where's the contact? Oh, is the contact patch?
Yeah, and then this is
Okay.
the ground. So
Okay.
this is 1 inch below this. And then full bump, this is like way up here, way above the ground, right?
Yeah.
So then from this, I then refound all of the hard points for the outer points. Like I retook their coordinates. Like if you like whatever, I took their XYZ coordinates for each of those points for the new positions. And then went through all those calculations to figure out the forces acting on them.
Yeah.
And then this is the original. This is what we did for Capstone. So green is at specific positions. Red is at ride height. This is a delta, so the difference between them, and then this is percentage change.
Okay.
So if we look at percentage change for now,
Right.
front upper, like 700% change, which would be like, what the hell? Why is it so big?
Right.
But if you look back over here, originally it was 10 newtons in the fore link.
Yeah.
And it went up to 80 newtons. So yeah, it increased by 800% or 700%, but it was a difference of only 70 newtons.
Right.
Whereas here, this went up by 36%.
Right. But it's like 2,000 newtons.
The difference,
it's 700 newtons.
Yeah. So basically, if we look at the color coding of this here, of this section here, we can see that the shocks more or less stay the same. Like they're like 10% difference in force.
Right.
But we get pretty big changes for the control arm loads, like the loads going through them.
Right.
So if you look here, this one went down by 23%. This one went up by 40%. And at first, it kind of doesn't really make all that much sense.
Yeah.
But then if you look at the assembly, because in the front, the shocks are at such a big angle.
Yeah.
As the control arm pivots up, the angle between the shock and the control arm gets smaller over time.
Yeah.
So more of the reaction force of the shock turns into axial loading versus bending on the control arm.
Okay.
You know what I mean? Like the triangle.
Yeah.
Let me. Fuck. Okay, this might get a little blurry. So dark black sketch here. This is original. We're looking at the front upper. As we rotate this up, this is going to swing up with it, right?
Right. Yeah.
So the angle between the shock and the plane of the control arms is going to get smaller and smaller.
Yep.
Oh.
Wait, sorry. So what do you mean by the plane is going to get smaller and smaller? What does this plane represent?
So this is this angle here.
Yeah.
Between the shock and the plane of the control arm.
Yeah. Okay.
So as we swing up, that's going to be going up to this point here. So now the angle between this and this is smaller
Right.
than this.
Yeah.
Which means a reaction force is going to be going like this. Versus this one is going to be going down like this.
Right.
And basically, that will mean you have more of the force going this way
right.
instead of this way.
Yeah. Which would induce, like, the first one would induce more bending, whereas this one would just be more lateral, right?
Yeah.
Okay.
So what that's saying is, assuming it stays at ride height at full bump, actually overestimates the force.
Yeah.
Which, for the sake of reliability, is not that important. For the sake of like weight optimization, you could make an argument that you could make it smaller and make it lighter.
Make what smaller and what lighter? Sorry.
Like the tubes, because we're actually overestimating the force by like 25%.
Right. And so we assume like ride height, or we assume that full bump would be the worst case usually for most of these situations.
For the jumps, yes.
Yeah. Okay.
Like in reality, it'd be good to know like the actual position of the control arms during a 6G jump. Like how much do we actually compress the shock?
Mm-hmm.
But without that data, I just assumed that it would max them out just to make.
Yeah, how do we even measure that? Like, do we just like get a video of the shocks like compressing next to like a ruler? Or is that like some sort of strain gauge and you just reverse you calculate the load coming from the shocks?
See, that's a good question. And what I think would be the most accurate way to do it would be to put a linear potentiometer on the eyelets of the shock, like on like both ends of the shock. You know what I'm saying?
Okay. Yeah.
And then sync that data up with the IMU data.
Mm-hmm.
And then look at those side by side.
I see. Okay.
So you can look at how much the shock is compressing in real time, or not real time, but like over time.
Wait, compared to the IMU data. Yeah. Okay.
So we've established that the fronts we actually overassumed, but the rears
get worse.
And they get worse because instead of the angle getting smaller, the angle gets closer and closer to 90.
Right. Yeah.
Which would mean more bending, less axial.
Mm-hmm. Yeah, and these are pretty significant in the rear too. Like 40% is no deal, no joke.
Yeah. Like it went from 4 kilonewtons to like 5.5 kilonewtons.
Yeah.
And then for braking acceleration, like
No
the
difference
percent,
basically.
yeah, like less than 10%. And that would make sense because for 1 inch rebound is the positions aren't that all that different from ride height.
Yeah.
Right. Like we're 1 inch off of ride height.
Yeah.
And then for braking, we can't brake that hard, right? Because we end up slipping.
Yeah.
The other thing to consider here is all of this calculation assumes that the forces are happening when the vehicle is level. Like we do have the load transfer calculation between front and rear based on the acceleration.
Right.
But the calculation for the link forces themselves occur at ride height with the contact patch being at ride height. So for this abuse jump, this is assuming the car is landing
gracefully on all four.
On all 4 tires on a flat surface, basically.
Okay. Yeah.
Which you can imagine like the projectile trajectory and the balance of the car. Like you end up nosediving and the front lands first.
Yeah.
So you may not get like 5.5 front and rear. You might get like 10 in the front.
Okay. That seems like something that is pretty alarming, no? Like, did you guys account for that?
No.
Okay.
The reasoning behind that was that a 6G jump is more than the car will ever see. So.
Okay.
But you can think of like where did I send this? I think I sent a picture. Yeah. Like you can imagine here.
Is that not when you did the rollover?
No, this is Julian driving.
Okay. Holy crap.
Like now we have the contact patch. Like if the car was driving, fuck's sakes. If the car is rolling straight or just landing this jump, we're assuming the contact patches are here.
Right.
And so all of this force is going like this.
Yeah.
But in reality, when you land jumps, like if the front is this way, like our contact patch is moving forward, and now all these forces are going up like this.
Yeah. Yeah. And so when we have the second situation, we'll like obviously we won't have as much travel in the shocks, and the load would be less in that patch direction, is what you're saying?
What I'm saying is we don't know how that will play.
Okay.
In terms of like it surviving.
Okay.
Like you can imagine that by moving the contact patch like forward, now we have a bunch of forces in X. So if we're looking at a top view of the control arm, imagine this is the tire. This is front.
Okay. Front control arm as well, or it doesn't
Yes.
matter?
So this is the front upper. So imagine the shock is like right here.
Okay.
This is front.
Yeah.
And in scenario 1 here, our contact patch we're assuming to be like right in the middle here.
Yeah.
But in scenario 2, our contact patch is now going to be like up here.
Yeah.
Which will try and rotate the whole control arm this way. Like it'll put a huge moment this way,
Mm-hmm.
which will make this hard point want to go that way. This hard point want to go that way.
Right. Which is not something you guys have calculated for, because then it's no longer, yeah. Okay.
And so here you might rip out the entire clevis.
Right.
Versus in case 1, both your forces would just be going in the same direction.
Right. Either tension and compression. Yeah. And so in case 2, it like the main failure mode would not even be in the control arms, is like your assumption is that?
Kind of, yeah.
Okay.
Like it could be in the clevis, it could be still in the control arm. Like I'm saying,
Right.
That we don't know.
Right. Okay. Yeah. It's definitely a more complicated load situation. Might just be useful to just get it through like a data acquisition system.
Yeah. The thing is with a DAC, if we have like strain gauges on the control arms and stuff,
yeah,
and on the clevises, like that information is useful and all, but you have to be able to build like a calculator to be able to interpret those numbers and give you useful information, which then becomes hard.
Is the calculator, it's like, what's hard about the calculator? Just like the matrix multiplications, or just like trying to calibrate the strain gauges?
All of it, like trying to get them calibrated and then interpreting the data, like the raw data from probably MATLAB or Python or whatever, I don't know.
Right. Okay.
And then turning that into like usable, like actionable decisions, if you know what I mean. Like taking that data and being like, okay, now what? We have our peak strain on a certain length during a certain event. Okay, what do we do with this information now?
Okay.
Like formula doesn't do any atoms car stuff. Like they don't do like a multi-body dynamics. And I think the reasoning behind that is because 1, it's a lot of work.
Yeah.
And 2, not a lot of people know how to do it. And 3, like they have, I think it's 1 inch of displacement on the shocks. Or the vehicle moves up and down an inch. So you can imagine like the geometry of the links doesn't change dramatically. So by assuming all those forces happen at ride height, like your magnitude difference between ride height and full bump won't be all that different. You know what I mean?
Right. Yeah.
But for us, we have like 8 inches of travel.
Yeah. Okay, cool. Is that your first year pick? Sorry.
It is.
Okay.
This is hub and upright stuff.
Yeah.
Julian can talk about it.
Yeah, I'll talk to him about it.
Clevis design. I didn't do all that much analysis on the clevises. I was planning on doing it by doing a full like corner simulation.
Mm-hmm.
instead of just like looking at the upper control arm, looking at the lower control arm.
What would entail in that sort of analysis? Like, what would you do if you had the time?
Basically, apply contact patch forces to the full corner and measure the reaction forces at each of the clevises.
Okay. Yeah.
Basically, see how the forces actually get distributed differently than our theoretical results.
Right.
And apply those to the clevises and see if like they'll rip out from the chassis.
Yeah, that makes sense. Yeah.
Basically, yeah. So like at first, basically I wanted to apply the link loads that we got from our calculator,
Mm-hmm.
and measure those at the clevises and then apply them directly to the clevis. But that is wrong because the clevises don't really take any vertical load. Most of the vertical load gets absorbed by the shock, right?
Right. Yeah.
So you just have like lateral, longitudinal.
Right. And so like you can also just not omit that value. You would have to redo the calc as well, right?
Yeah, and you don't know how they all play together because it's the whole system and like the upper and lower together versus just looking at the upper, just looking at the lower.
Yeah.
So then I wanted to do a full corner model to address that, but it was too hard and too long and I didn't have enough time. So we scrapped it. And I think in the third version, yeah, just went through and said, disregard your vertical force and the X and Y forces.
Okay. Yeah.
But I don't even think I ended up doing any simulation on the clevises. I just said it's good enough. Like they're 1/8 inch, like mild steel, like rectangular and square tubes that we notched around the chassis versus being like just two flat plates or like a boxed in, bent, and welded plate.
Right.
So it's like inherently this design is already better than it was in the past.
So you mean like square tube, like it was actually like from a cut piece of tube?
Yeah. So like if you look at this is like an actual tube that we notched to fit onto the chassis.
Oh, so
like it's all one part.
Where'd you guys get it from? Metal Supermarket?
McMaster.
Okay. Sorry.
So after doing all of our analysis and stuff, we decided to do an actual clearance study to make sure we don't rip any boots and we don't break any like rub on tie rods.
Yeah.
So Kevin made like a flexible assembly. And basically we're looking at heim joint clearance for all steering and all suspension travel.
Okay.
Basically making sure we don't max out the heim joints.
Yeah.
Because on the previous car, like you remember how we would have to deflate the shocks to be able to put them in?
Yeah.
That was because we would max out the heim joints at full the shocks.
Okay.
Or we'd max out the heim joints before full extension.
Before the shocks could max out.
And so the only way to put the shocks in was if you compress them.
Right.
In the bigger picture, this means we're not actually getting the full travel that we designed for.
Exactly. Yeah.
And we also crash into the heim joint every time the shock extends.
Yeah. So how did you guys how did you end up calculating this? Was this just a manual thing? You just like clear through the travel in
Yeah.
SolidWorks? Okay.
Yeah. Look through the travel and make sure the Heim joints don't get maxed out. So like, if you look here, this is like the axis of the
Wheel.
the wheel.
Yeah.
So before these were parallel to try and make it on like a 3-axis machine.
Yeah.
But you can see here, like you have interference, like the Heim joint gets maxed out and here.
Yeah.
So by angling them upwards, we were able to figure out a balance that we don't interfere at full droop and full bump and steering.
I see. Does that not interfere with your calcs? Like, does that not change how your control arms or the loads get put into your control arms?
No, because the physical point in space, basically, I think this will make a little bit more sense here. If we look at the hardpoint files, like the actual points here, like in the sketch, represent the middle of the Heim joint.
Yeah.
So in space, is this the updated version? No, this is not the updated version.
Okay.
Basically, the point where the Heim joint is in space stayed the same. It just, the geometry around it changed.
I see. Okay.
I think it makes sense here. Like if you look at the center of the Heim joint relative to this point.
Yeah. Oh,
like
I see.
like,
I see. Yeah.
Like
yeah,
it's
Wait.
that
So
big
this would
there.
not affect your control arm geometry, but it would impact like your KPI, right? Because now the control arms are fundamentally at different angles, or to the relative to the upright. Okay. So the control arm position is staying the same, and then the upright position is also staying the same.
Yeah, it's just the geometry of the upright changing.
Is different. Okay, got it.
So if we were to draw a straight line through this,
yeah,
and we take a straight line or whatever the wheel center plane is,
yeah,
the angle between these two, that's our KPI.
Right.
And then if we were to look at the side and plot the same line through both the upper and lower Heim joints versus the vertical line, that would be our caster. Basically, the Heim joint stayed the same in the same position, just the flanges that it mates to rotated.
Okay. Yeah.
So the geometry all stayed the same, like suspension geometry stayed the same. Just
I
the
understand.
Upright.
Yeah, I understand. Okay.
And then we increased the track width by 20 millimeters to be able to use 2 single row ball bearings.
2 what ball bearings?
So in the past, we used a singular
giant
double row.
Yeah.
Versus now we have 2 single row bearings that are spaced out.
What and what is the between the bearings? Just like a spacer?
A spacer, yeah.
Okay.
And so this makes it a lot more stable and a lot better, a lot less bearing loads.
Why would that need to change your track width?
I think it had to do with packaging the caliper in with the rotor. Like it was just too close to the hub, to the space of the hub. But you can see the clearance here.
Yeah.
Like we needed to space that out a little bit more to be able to fit the caliper in here.
Okay.
So you basically just shifted everything out shifted the contact patch and wheel center out by 20 millimeters. And so we recalculated our forces and reran FEA, and then it was like a tiny bit different. So we're like, all right, whatever, screws. It's like we shouldn't bother doing a new analysis over again, just because the difference is so small. Okay. The other nice thing about these new hubs is, like in the past, we would rely on the castle nut here to squeeze the whole assembly together to prevent the hub from coming out.
Yeah.
But if you see this plate here with 4 holes, so this is just a thin sheet metal plate that caps over the hub and pulls against the inner race of the bearing here.
Okay.
So that basically prevents the hub from flying out.
But like, so this would only work if the half shaft wasn't in.
Yeah, basically this lets you run
it. Okay.
2-wheel drive.
Okay. Yeah, got it. Sick. And then do you have like a little shoulder on the other side of the wheel hub to prevent it from coming out the other way, right?
Yeah.
Yeah. Okay.
And we got new wheels with a smaller lug pattern before we used
big boys.
4x4 inch. Now we're using 4x101.6.
Okay.
Is that not the same? Anyways.
It's 4x156 versus 4x101.6.
Yeah. Basically, that makes us we don't have to use such a big piece of like stock.
Yeah.
And so Formula donated stock for us to use. So it was basically free. Instead of having to buy like $2,000 worth of stock.
Right. Well, the front wheel hubs are long.
Yeah.
Oh, because of the calipers.
The calipers and 2 rows of ball bearings.
Yeah, okay. Does the rear also have the 2 things of bearings?
Yes, but it doesn't have a flange for the rotor.
Yeah. Okay. Does the rear also have the bracket as well, or
it has those holes.
Okay.
But
cool. I guess if we're ever rolling it over, we don't have the power trim in. Nice.
Yeah, and then this is Julian's FEA stuff, but I don't really want to talk about it because I didn't do it.
Yeah. Okay.
Yeah.
Thick.
This is a long haul.
Yeah.
Let me pause the recording.
Feel long?
No, not really. It just felt like I was yapping. Ugh.